Yeah, so good morning, good afternoon, good evening, everybody. I'm seeing people rolling in for this webinar. And we have a wonderful speaker today. It gives me great pleasure that I've managed to entice Michael Pyrcz to speak to us about machine learning-based geoscience. But before we introduce Michael, just a reminder for some of you, but if some of you may be new here, this is a weekly webinar series run on Wednesdays from October to June. And you can go on this webpage and you can see their registration links and of upcoming webinars and the links for the recorded webinars of past ones and presentations. And we still have 3 open spots. This is an advertisement. We're looking for people to give us talks in November and December. You are on a Zoom webinar, so your controls are to send a message to the panelists. Raise your hand if you want to speak at the end, and we encourage this, we encourage dialogue. And then please send your questions in the Q&A. And Michael, if he has time on the fly, he might answer a question if it's a short one, otherwise they'll be answered at the end. And a quick advertisement for the 3 EMinars coming up in the rest of November. Next week, Mengli Zhang, the week after Irfan Akka. Then we have a gap when we're looking for a webinar to fill as 23rd November. And then finally, Chushan Lu on geometry inversion. But today we have Michael Pyrcz, also known as the Geostats guy. And I've been following Michael's work for about a year now on his YouTube channel, and all the material he makes wonderfully available. And I'm learning an awful lot about geostats and downloading Python codes from the GitHub and so on. So Michael, those of you who are registered will have read the CV, so I'll very quickly get over this because I want to give Michael the most time. Associate professor is actually from Canada, which is wonderful. Associate professor in Texas at Austin. Principal investigator of the Energy Analytics Freshman Research Initiative, a machine learning laboratory. He's written over 60 peer-reviewed papers and a Python package for spatial and subsurface data analysis. So I'll end there, Michael, and let you take over.
Awesome. Thank you very much, Alan. I appreciate the introduction. I really appreciate the opportunity to be here. I really appreciate the idea of like on-the-fly questions. I love interactivity, even if we're in this kind of virtual world and so forth. I think it's really nice to have the opportunity to get questions during the discussion. So what I'm going to do is I'm going to have the Q&A window open. I'll have the chat window open. I'll have the participant window. I'm opening up all the windows. And so if anybody wants to interact with me, even thumbs up, you can give me a thumbs up and I'll see it on the attendee list here and all that. So I love interactivity and I do appreciate that. Thank you so much. I want to just right off the bat here, I should give an acknowledgement. And that is I will be sharing examples. And of course, all professors stand on the shoulders of great students. So I want to be very clear about that when I'm demonstrating methodologies in data science, machine learning, and data analytics for the subsurface and geosciences, I'm going to be using work from some of my students like Hongong Zhou and Penn and others. And I really appreciate that. The other thing too, every professor always walks around their hat in their hand all the time. So if anybody sees the work here and you work with a company and you're like, we'd like to collaborate, we would like to hire an intern, full-time hires, reach out to me. I'd be more than happy to discuss the students and opportunities for collaboration. Also, I want to acknowledge I collaborate a lot with other faculty. I'm appointed both in the Jackson School of Geosciences here and also the Cockrell School of Engineering. And the faculty down here in Texas have been super fantastic as far as working across different specificities or specific disciplines and working together and solve tough problems. I want to acknowledge the professors that I work with. Alan Jones and others, thank you so much. I do appreciate Lindsay and everybody for setting this up. It's really a pleasure to be able to speak here. And the main thing I want to share is this, is that there's a great opportunity for interaction between what we call artificial intelligence or data science and data analytics, specifically machine learning, with geoscience and subsurface engineering, the practice and the research. I think there's a chance to put it all together. I'm going to make arguments and defend that statement and demonstrate it all the way throughout today. So that's my goal today. Academia and industry, I just want to comment on the fact that you may listen to me and think, wow, this doesn't sound like a professor. You're kind of right. I've only been doing this for about 5 years. I did spend about 13 years in oil and gas, subsurface engineering, and so forth, working in research and project management and so forth. So I've done a lot of that. Also now, as a professor, I do a lot of teaching in companies. Actually, what's really funny, yesterday, I taught all night. I was teaching the night before last night. I was actually teaching all night in Middle East. So I do a lot of teaching inside of companies, but I do have a good research program, about 15 graduate students working with me right now. So the other thing is, and Alan, you already said this, I want to just emphasize this. I do share all of my university educational content, which includes well-documented workflows, interactivities. Here's an example right here, right from one of my lectures, where I demonstrate DB-scan, density-based clustering analysis. And if you're interested in learning about spatial data analytics and geostats, well, here's a methodology right here where I demonstrate sequential Gaussian simulation in Python. I've even developed like a Python package for geostats and for, quantitative geology. So I do provide a lot of this content. It is available on my YouTube lecture series, which I have all of my courses organized by playlist: machine learning for subsurface, subsurface modeling, advanced geostats. And I even have a course in data analytics and geostats basics that goes, Alan mentioned he's going through it. So it goes all the way from fundamental probability, frequentist and Bayesian approaches, all the way up to how do we do like co-simulation and methods like that, decision making. Also, all of my workflows, like hundreds of well-documented workflows that support all of my courses and the interactivities, are all available on my GitHub account. Just look me up. I'm I think I'm one of the few Pyrczes there, or Geostats guy. You'll find my GitHub account with like 39 repositories full of lots of really useful code. I hear from people every day who are using this in industry or in the middle of their PhDs. If it helps you out, please go ahead. Let me know. I love to hear about that. Okay. All right. I just got a thumbs up. I appreciate that. Thank you very much for sharing that thumbs up. I do appreciate it. If you guys have any interactions, Alan just made an announcement on the web chat that if you have any questions, go ahead and just fire them off and I'll answer as we go. Okay. So what's the opportunity here? There's been a big recent wave in artificial intelligence. In fact, it's hard to read a peer-reviewed publication or go to a conference or anywhere you go, engineering, geoscience, whatever, you're going to hear about artificial intelligence and data science. It's just a big wave right now. And yet the subsurface is unique. And many of our problems are not the same as Spotify or Amazon or something like that. But what's really interesting, in many ways, we progress further along the digital transformation. In fact, what I'll say is that we are the original data scientists. I believe that. We in the subsurface have been doing this for a long time. And we can offer useful insights on the path ahead for the merger of science and engineering with AI. So we have a great opportunity to support others. Okay, this is what I'm going to cover here today. I'm going to talk about geoscience and subsurface engineering. Okay, I'm just going to remind us, the group, we know. I'm going to talk about what we already know, and I'm going to remind us of data science concepts. And then I'm going to talk about what we're learning, new research using machine learning and data analytics. So let's see how this goes. Go ahead and jump in with questions anytime. What is subsurface resource engineering and geoscience? And I love using a diagram like this. I think it's really helpful. The way I would describe it is that we work with vast, sparsely sampled heterogeneous systems. I like to remind my students that we sample volumetrically directly about 1 trillionth to 1/100 billionth of the volume of the subsurface of the volume of interest. We have to integrate various data and information sources over many scales. Ours is a challenge of data integration. It's a wonderful challenge, but we have expensive, high value, high impact decisions to support. Okay, and so because of this, we've developed great workflows. Anyone who looks over here on the right-hand side is probably familiar with a bunch of these elements. The idea of having different types of data at different scales. I show sections representing stratigraphic interpretations. We have seismic data is probably informing specific horizons and correlation styles that are interpreted from seismic facies. We got wells with all the logs that are available. We do our well log combined and anchored with well core analysis. We work out what are the specific architectural styles and the hierarchies, and we put it all together within that seismically mapped structure. We're going to go ahead and do statistics. We do a lot of spatial data analytics. We do trend modeling. That's very important to everything we do. And then we have a residual where we do varograms. We do other types of quantification of spatial continuity and heterogeneity measures. We use all of that characterization, then reproduction to build multiple realizations conditioned to all of the available data streams, which is very, very important. And all of that, those realizations are piped through a transfer function. What's the transfer function? It gets us closer to dollars. That's what it's all about, right? It's volumetrics, flow simulation. What's the recovery rate, the estimated ultimate recovery, whatever it might be, it gets us a distribution, an uncertainty distribution that we can use to support decision-making in the presence of uncertainty. What do I tell my students? If all of your work does not impact the decision, you do not add value. Oh, that sounds kind of harsh. I should be nicer than that, but it's true. It's true. Okay, so this is the workflow we use. And because of our challenge, we've been doing it data-driven the whole time. In fact, what I like to tell my students, and I'm proud about this, is that we are the original data scientists. We've been doing data science long before tech companies even existed or knew what data science was. 1930s and 1940s, probability concepts were being developed. Do you ever wish you could go in a time machine, go back in time, go back and review Kolmogorov's statistical probability axioms? We could figure that out. Probabilities must be greater than zero, probabilities sum to one. This is stuff we could have figured out, but it's fantastic, right? Fundamental probability concepts, 1930s and 1940s. And then, of course, you get into the 50s, and you got Krieg and Sichel, and all of them were doing kriging. They were developing these methodologies, of course, which were mainly around how do you estimate in space so that we knew where to drive the drift, where to mine to maximize grades recovered, and how to model that in space. Well, of course, later on, Matheron came along and developed the theory and coined the term geostatistics, which I like to say is just spatial data analytics, an important branch of data science. And so applications of oil and gas and environmental, well, then we cite people like Andre Journal, Verily, and we've got, of course, Clayton Deutsch, my PhD advisor. Shout out to a great Canadian professor at University of Alberta, for sure. And then we go ahead and we get into kind of modern context of people talking about spatial statistics, big data analytics, and machine learning. And we recognize humbly that we're probably in the fourth wave of machine learning with a lot of great machine learning developments back in the 80s and so forth, and even earlier. So what do we say? We say we have complicated, heterogeneous, sparsely sampled, vast systems with complicated physics and high-value decisions, and it drove us to early adoption of the fourth paradigm approach, data-driven approaches to learn about our natural setting, to learn about the world. Now, what do I mean by fourth paradigm approaches? Well, if nobody said this to you before, let me welcome you to the fourth paradigm of scientific discovery. Did you notice? Yeah, it's been going on for a while. In fact, if you want to argue 2010 is too late and you want to say it was earlier, I won't argue with you. We can say 1980 or 1990, that's fine. But the first paradigm, what was that? Experimental. This is the whole empirical science approach. This is using experiments to understand the world around you. Now, if you go back in history, well, ancient Greeks, the Egyptians, and others were doing some pretty wicked, cool experiments. I don't know if I'd want to be part of some of their medical experiments. I know they dig up bones and find there's holes cut in skulls and so forth. Yeah, I'm not sure if I'd want that. But the second paradigm, theoretical science. This was the idea we take the experiments, we could fit functions, we'd start to understand the laws, which is a big step forward, you know, Renaissance and so forth, Enlightenment, a lot of cool stuff going on there. Third paradigm, that's when we realized that the world is heterogeneous, the geometries are very complicated, and everything's coupled. So you can't just use analytical expressions. You have to pose it as a numerical model and simulate it forward to see how it behaves. So this assimilation, of course, the rise of computational resources opened those doors. Data-driven science is all about the fourth paradigm approach. This is where we use new developments in algorithms combined with new data streams. We have a lot of data now available we didn't used to have, combined with a lot of new powerful computational resources. You put that all together and we have brand new ways to use artificial intelligence, machine learning, data analytics approach to be able to detect anomalies, to be able to find patterns, to learn about the data, to learn how to play games even better. That's pretty fascinating stuff that goes on there. So there's a lot of really cool things, powerful things, self-driving cars, that are going on with the fourth paradigm type of approach. Now, if you work for an organization or if you're in school, and you hear about digital transformation and new technologies in your field, geoscience, and you're like, wow, this is wild. Remember, you're not alone. None of us are alone. This is going on everywhere. In fact, Deloitte did a really good study. I was asked to participate and to give some answers or survey on this. They did a study, broad study, and what they found was that when they looked across different sectors of our economy, there were different levels of readiness. And the way they rank that is by the proportion of organizations with high maturity of the use of data science methodologies. And when they looked across, they ranked them, they found sectors like TMT, tech, media, telecom, they were near the top. They're on the bleeding edge. They can have that. That's fine. Then we get down to like energy, which I think energy would be a great descriptor of geoscience, right? So energy or geoscience type of areas tend to be somewhere in the middle of the pack. Life sciences and healthcare tended to be kind of near the trailing edge. So all sectors of our economy are going through this transformation right now. But what do we say? We as geoscientists, we as subsurface engineers, what is our message? And our message is, we don't replace the prior paradigms of scientific discovery. Please, for a moment, just consider the second paradigm. Anybody here who's been involved and worked with classical laws, you can see immediately, it's readily apparent that it was developed through experiment, that it was experiment that was used to kind of support its development at every step and confirm it. Then if you go to the third paradigm, well, anybody here involved in computational simulation knows that not everything has an analytical expression. Not everything has a law. In fact, what we may find ourselves doing, I know at one point I was involved in the simulation of turbidite flows into deep ocean basins. We didn't have an analytical law-based approach to what's the entrainment rate of sediments into the flow. We went to flume experiments and we looked at observations from empirical science to then be able to condition our numerical simulations. Okay, so we can clearly see that computational science is built on the second and first paradigm. So the fourth paradigm is going to augment with a new scientific paradigm, a new lens or perspective by which to see the world, but we don't replace the old paradigms. What's the potential path for digital readiness? Now, let's go from kind of the sector of the economy and that type of scale. Let's scale down to you as an individual. What is your path to digital readiness? Now, if you Google data scientist, I want to be a data scientist, I guarantee you in short order, you're going to find this Venn diagram right here. The Venn diagram tells you that you need to have domain expertise, statistics, and knowledge of the algorithms associated with statistical modeling and coding. Sometimes they say hacking, scripting, some type of knowledge of how you put together the workflows. Okay, the streams, the pipelines, whatever we want to call it. Okay, so what's interesting is they say that that unicorn or that individual has all of those capabilities is a data scientist. What I say to you, and I've taught a lot of geoscientists and engineers data science, I say to you is that the domain expertise is the most important. And what I would say is that we should continue to grow that domain expertise. So I scale the circle, I make it bigger. I'm communicating that it's the most important aspect. Then what I say is that we in the subsurface already have a good knowledge of a lot of numerical methods. I can't find a geoscientist who's not building PDFs and CDFs, who's not going ahead and building some, predictive models, doing some type of quantification of their observations from the field. So what I say to you is build on that. Continue building your knowledge of statistics. We have great knowledge. Many of us know geostats. Build on that. Build up use of robust statistics and data curation. Okay, next, many of us do have a little bit of an issue of coding. I know that, and I've taught enough geoscientists, but have some enthusiasm. Be willing to learn a little bit more coding. Look at it from the perspective of not a joy of coding, but a joy of building the workflows. Workflow construction, hey, coded workflows are great. Automation, great workflow documentation for future you to understand and remember what you did a couple of years ago. It's a wonderful thing to do. This is what I suggest for your path forward to digital readiness in your personal life. Okay, so what am I saying? What's my summary here? We were driven to early adoption of data-driven approaches. The fourth paradigm, it was happening for us early. It means that we've gone further down the path than many of our science and engineering brothers and sisters, which is super fantastic. We integrate all scientific paradigms. Continue to grow your capabilities in your scientific domain. Please, we do not use machine learning AI as a crutch instead of learning the fundamental geoscience and engineering. We succeed by building on our geoscience and engineering strengths, for sure. Okay, that's geoscience and subsurface engineering with reflection on digital transformation. What do we already know? What I'm going to do now is I'm going to offer some bridges. I'm going to go through and talk about a variety of concepts that we know that are related to data science concepts. I think this is really exciting. First of all, big data. Okay, let me ask you guys. I see the participant window open right now. I should see your hands if you put your hands up or show me a thumbs up. How many people in attendance right now work with big data? How many work with big data? Show of hands, thumbs up. Nikolay, I see that. Anyone else? Enrico, I saw that. Okay, I'm seeing some thumbs up going up. Awesome. Augusto, thank you very much, everybody. I see a few of us already. Now, to those of you who did not put your thumbs up or your hands up, let me see if I can convince you that you may already work with big data and not know so. Big data, how do you know? There are multiple V criteria that we use to determine if you work with big data. If you have enough of the V's, we'll go ahead and we will give you a patch, we'll give you a badge, and we'll say you work with big data. First of all, volume. Who here works with many data samples that are difficult to handle, difficult to visualize? If you do that, then you can check that box, you have volume. Velocity. Now, the tech people, I think they're a little snobby about this. The tech people say it has to be real-time data. No, I push back on that. If you work with data with a high rate of collection, in other words, it's continuous relative to the decision-making cycle. Now, think about the complexity of your decision-making cycle. If you work in mining, if you work in oil and gas, if you work in forestry, there's some complicated things you have to do every time you have new data. It's not just put it in the model and see what happens, right? There's a lot of layers of interpretation. There's human interaction. What I would say is what I've seen in energy is that we are always running with our models to keep ahead of the bit. In other words, we have velocity. We have a high rate of collection. Variety, do you have data from various sources with various types and scales? Oh my gosh, do I have to even say anything here? We could have thin sections up on the screen where we're looking at pore structure and cementation alteration patterns, and we could go all the way to basin analysis. We can look at entire basins. You'd see that from space. Like, imagine that. That's incredible. We check that box, variety, for sure. Proudly, we check that box. Variability, data acquisition changes during the project. We have this too. Oh yeah. Anybody here ever worked with two-dimensional exploration, seismic, or any type of remote sensing data? And then when you start to actually get into an appraisal stage, maybe you get to three-dimensional modeling of it, right? Three-dimensional. And then if you're in energy, there's been a lot of stuff going on. You know, you put ocean bottom nodes in, deep water, and boom. Pop the popcorn, melt the butter, you're watching a movie. You're watching four-dimensional, you're watching the fluids flow, the hardening structure patterns as fluids, oils being replaced by water, a hardening pattern in the seismic. Very, very cool. Veracity, check that box. We have variability. And then veracity. Data has various levels of accuracy. Let me ask you this. Can anyone tell me a single data type that we work with that has no uncertainty? Anyone? Anything we work with no uncertainty? I don't think you can. I don't think there is. I've asked that question to hundreds and hundreds of students. And one thing I'll hear is this: oh, production data. So oil and gas production. And then somebody else will stand up in the classroom and they'll say, wait, the meter has an error. Okay, it has some error, sure. Where did the production come from? Do we do PLT? Do we do some type of production logging tool where we know exactly where the production's coming from into the wellbore? No, we don't. We rarely do that, and that has error too. And then even if we know where it comes from, do we know where it comes from outside of the wellbore? No. There's uncertainty with everything we work with. Check all the boxes. We work with big data. Everybody, I hope everybody who works in the geosciences now can put up their hands, update your CV. You work with big data. Okay, what about statistics? It's all about collecting, organizing, interpreting data, as well as drawing conclusions and making decisions. What's data analytics? Google search that for fun. Analysis of data to support decision-making. Wait a minute. That's statistics. In fact, what I would suggest is that data analytics is statistics. And I've said that in many public settings, and people usually clap. People agree. Spatial data analytics, well, that's just geostats. Or as spatial statistics, that's fine. I know some people want to differentiate them. I don't think so. This geostats people have always been very inclusive. If what you do supports modeling spatial phenomenon, we'll call it geostats. We've always done that. What is machine learning? Well, you could Wikipedia search it. Yeah, sure. It's a study of algorithms and mathematical models. You hear the plural? It's a toolkit, multiple algorithms. Computer systems used to progressively improve their performance. They're learning. On a specific task, machine learning algorithms build a mathematical model of sample data known as training data. Okay, toolkit algorithms that learn from training data in order to make predictions or decisions without being explicitly programmed to perform the task. Okay, they're general. One algorithm could work on a problem like data imputation, feature imputation, when you're missing some data along your borehole or your drill hole, or you could have a problem of pre-drill prediction elsewhere. Use the same machine, it should be able to work. General. Where it is infeasible to develop an algorithm of specific instructions for performing the task, that's at the very end of the article. A lot of people don't read all the way through. What's it telling you? It's not a panacea solution. In other words, if you in fact know the engineering physics, if you know the geoscience processes and concepts and physics, and you can build a model of that, do that. Don't jump to data-driven approaches if you understand the natural phenomenon. You gotta balance this. Don't use data science as a crutch instead of learning the fundamental geoscience and engineering principles, concepts. What is machine learning? Well, a prediction machine learning model, every time you hear that, please think of this equation right here. All you have is you have a set of inputs. Those are predictor features. That's what they call them nowadays. If you're old school statistician, you call that the independent variables. Same thing. It's the model inputs. You have the response feature, the Y or Ys. It's going to be the response features, and the old school statistician called that the dependent variables or variable. It's the model output. And F is going to be your model. You can have some type of allowance or model for error because we expect that. We don't perfectly match our training data. Machine learning is data-driven statistical learning. Now, what's the general modeling workflow? And the modeling workflow is really quite intriguing if you look at how you build a predictive machine learning model. And the first thing I'd commented is this. Okay, I just saw a question. Oh, I had a spelling check. Hey, Jerry, thank you very much. I do appreciate that. I don't know why it is, but every once in a while, I misspell principles and principles. I don't know why I do that, but I've done the same thing with my PCA course. I found a couple times that I put LES. So thank you very much for correcting me on that. Okay. So here is the general modeling workflow that we use. And that is to build a predictive machine learning model. What you're going to do is you're going to take your data. So we got a simple problem. One predictor feature, Z for my Canadian, Z for my American friends. which is just a coordinate in space. It's like we're trying to build a machine learning based trend model. We got permeability. So this looks like an oil and gas example here. We got all of our data here. You're going to take your data, you're going to split it. You're going to take a portion of the data, usually about 15 to 30%. You call it testing data. You're going to take it and you hide it. Now, do you have a place in your office where you don't go? You have a pile of papers. You know, it's got kind of a low, what I like to call a low energy sedimentary environment in my office. Go there and stick that data under there and don't look at it. No peeking. Okay. Now what you're going to do is you're going to take the training data that you keep, the X's, and you're going to go ahead and you're going to fit a simple model. So imagine a linear regression model. You fit that simple linear regression model. You change the model parameters to get the best fit with the training data. Then what you do is you increase the complexity of the model. If you're doing a linear model, why not you do a second, third order polynomial model? Okay, do that. You fit now you've got what? The third order is going to have 4 parameters, right? B3, B2, B1, and the intercept term. Go ahead and get those to minimize the error with the training data. Okay, and then you have a 5th order polynomial, a 7th order polynomial, and so forth. Now what you're going to do is you have all of your models fit to different levels of complexity, which we'll introduce as hyperparameters right away. And then what you're going to do is you're going to take the testing data. Remember where you put it? You're going to bring it back. The circles are back. There they are, testing data. You're going to see how did your model perform with the testing data. You're going to calculate the distribution right here. And when you do that, you're going to look across all of your model complexities, the hyperparameters, and you're going to find which model fits the testing data best. What are you doing? If you pick the model that best fits the training data, which model would you pick? This model, this model, this model, this model. Look at this. By the time you get to a 7th order polynomial, you can perfectly fit the testing data with no error, but your performance at the withheld, you can fit the training data with no error, excuse me, but your performance at the withheld testing data right here, 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 and here is terrible. In fact, right here, I apologize. The model's punched through the bottom of the screen. It's gone through your floor. It's probably damaged your desk. It's a very, very bad model, right? So what are we doing here? By picking the model that does the best with the withheld data, it's a dress rehearsal. We're seeing which model performs best in prediction problems not used to build the model. And so this is called hyperparameter tuning. Now, I've said a bunch of terms. I should kind of define them, and I should make a couple of comments around it. And the first thing is this, is I should acknowledge the fact that the hyperparameters are anything that constrains the complexity of the model. So in other words, it's just going to be, is it a 1st order polynomial, linear, 2nd, 3rd, 4th, 5th order? That's the hyperparameter. Okay. Parameter of a model, that changes the fit. So the coefficients of the polynomial, that's the parameter. So I just want to make sure I'm clear when I talk about training model parameters, what a parameter is, tuning model hyperparameters, they're controlling the complexity, what they are. Okay. Let's talk about numerical optimization. So it turns out that when we do machine learning, we have to do numerical optimization. It happens all the time, in fact. We have many machine learning methods that are solved by optimization because the loss functions, the norms, and the specific configuration of the problem are such that we can't just do partial derivatives and set it equal to 0 and then find the actual equation for the parameters. You can do that for linear regression. As soon as your norms get kind of complicated, like a lasso regression or where you have an L1 norm in the regularization term, you can't do it anymore. So you're going to have to do some type of iterative solution. Now, the good thing is this, is that many of us scientific people, scientists and engineers, we do optimization. It happens all the time. In fact, you can take your loss function and for fitting the model, and you can go ahead and iteratively do a steepest gradient descent, and you can converge on the optimum model parameters. Or if you have too big of a step size, you'll diverge. But at least we understand this concept of optimization. Okay, what do we already know? We already work with big data. So guess what? Not only are we the original data scientist, but we already have been working with big data for a long time too. Data analytics is statistics. Update your CV. if you do statistics at work, if you do spatial statistics at work, now you do data analytics, you do spatial data analytics at work. Okay, machine learning is statistical learning. It means the fundamental concepts of probability. I don't start a machine learning course without spending days on frequentist and Bayesian probability. Geoscience and engineering concepts are core to everything we do. Domain knowledge, trend modeling, optimization, how do we extract information from our data streams? All of this is critical to everything we do. Okay, what are we learning? Let me just stop here. How are you all doing? Everybody good? Everybody still have some energy here? Can I get a thumbs up here if you're still good to go? There we go. I'm seeing some thumbs up. Hey, thanks a lot, you all. I appreciate that. Hands up too. That's fantastic. Thank you very much. That's wonderful. I really do appreciate the participation. Let's carry on. Let's talk about some things that we're learning. Now, this is a little bit shameless because I'm going to focus on work from my own students. I'm going to acknowledge that there's great work going on all over the country, all over the world in these topics, and I could have done a better job being representative. Let's face it, it's my students. I want to promote my students. Also, I can grab the figures directly from their papers. It was very convenient. Rapid fire, let's talk about some lessons learned. Machine learning to assist with subsurface interpretation. And subsurface interpretation to assist with machine learning. Okay, what's really interesting is this. We know that there are characteristic or common patterns in well logs. And we know this because we go to outcrop. And we know, for instance, if you're in a deep water setting and it's unconfined turbidite flows, that you expect a thickening up pattern due to the fact that you have a natural progradation of the lobe system. So you're going from marginal lobe to axial lobe. Okay, patterns like that are well known and demonstrated. In fact, you can go to standard textbooks and you can find great illustrations like this, channel point bar deposits, delta progradation, and so forth. There's a thickening up pattern there, right? Okay, so we have these kind of known patterns. And so what we did is one of my students actually went ahead and did a training of convolutional neural nets on these types of patterns. And then what we did is we went to available data and we used the convolutional neural net to determine the depositional setting. What did we find? We found that feature engineering was essential. In fact, raw quality index was a great way to convert the input data, the predictor feature, to something that would be better informative for the convolutional neural net. The other thing we found was this, and this is really, really interesting, is if you take a convolutional neural net and you just feed the data, the well log into it, you're going to find that the accuracy will be pretty low. If you use some type of interpretation where you're using available stratigraphic correlation between wells, in other words, we're starting to bring in multi-well spatial correlation, and you separate the data up, segment it like that, and feed that into the convolutional neural net, you greatly improve the accuracy of the machine. What's that mean? What we're finding is that many of our machine learning workflows work better if there's a hybrid where we work with an interpretation framework to support the machine. Okay, so that's really interesting to us. Deep learning, just like geostatistics, which is another data-driven approach, a fourth paradigm approach, really works best within a interpreted framework, which is based on the geoscience and engineering knowledge. Okay, what about feature engineering? And this is really interesting, is that we build the best possible machines when we engineer our features. What's feature engineering? The definition is you make new features that are incorporating domain knowledge. You're correcting for bias, you're correcting for representative sampling, you're correcting for adding physical or spatial information. Okay, so what we did is something really simple. Wendy Liu, one of my PhD students, actually just graduated and is working now. Congratulations, Wendy. Is developed this really cool idea. Dispersion variance is well known in the geostatistical community. In fact, I could cite really good work from Peter Frickman and Clayton Deutsch and others who have done a great job kind of demonstrating opportunities to use this in our field. Okay, so here's the idea. We know dispersion variance is a general form of variance. The variance we use is actually a specific case of dispersion variance related to the idea of just point data and no spatial context, in fact. Dispersion variance will account for the scale of the data and will account for spatial continuity. And so what we've done is we said, why don't we engineer a new feature, which is if you have a well or a drill hole, figure out the volume of influence, figure out the volume sampled by that data, and now calculate the dispersion variance over that. That's a variance that represents the amount of heterogeneity, and it's accounting for spatial continuity. In other words, it'll change if you change the orientation of the data. Like imagine a horizontal well, if you rotate it, if spatial continuity, primary direction, the major direction is this direction, it'll change the degree of heterogeneity seen by dispersion variance. What we did is we actually put that into as an engineered feature into a forecast model for flow production in unconventionals, and we got a good improvement. It actually was a very meaningful feature. Okay, so let's use our knowledge of spatial domain, geoscience, engineering to engineer our features at every step. Okay, so that's critical what we do. What about ideas like this, dynamic time warping? Maybe we can treat our problem as a signal matching problem. And I really like this. If I go back to an oil and gas example, you have injection of water shown right here. You inject the water first, and then what you're going to have is you're going to have production of hydrocarbon at a neighboring well, injectors and producers that are coupled. And so what we can do is we can use dynamic time warping to be able to try to map between those two signals. If we do that, now we can understand the relationship between a location space and a location in space. We inject water here. How does it respond here with hydrocarbon production? You understand the degree of tortuosity and heterogeneity. You can understand the degree of effective versus dispersive type of action in the water piston as it's flowing. Is it piston-like flow, or is it getting more distributed, more dispersed? Okay, now what we found that was really interesting is when we did this, the dynamic time warping can correlate backwards in time. In other words, you get the causal mixed up. You could have water injected causing previous hydrocarbon production, which is paradoxical. That can't happen. So what we actually did is we imposed a constraint in the cumulative cost matrix, which is the graphical method to solve dynamic time warping. And we did that. Something fascinating happened is we ended up with a physics-constrained dynamic time warping. Okay, so this is what I want to suggest. Every chance we're doing machine learning, look for opportunities to constrain with geoscience and engineering constraints, and you'll find there's great opportunities to do that. Garbage in, garbage out, bias in, bias out. So we in the geoscience field know bias, and actually we're really good at this, right? Like Andre Janel, development of cell-based declustering. What was that? That was like an appendix in a great paper already. GeoSLib, Deutschen Journal, common practice, cell-based declustering, the declust program, right? And then there's polynomial declustering, there's kriging-based declustering. We've been doing declustering for a long time with spatial data. People who do hydrology do declustering for when it comes to rain gauges and their sampling rate in space. Okay, so we know that there's an issue. And so what we said is that we know our spatial sparsely sampled data sets are going to be biased. We know that in geostats, we have to decluster. What about machine learning? And so we took a very simple machine decision tree. We had two predictor features, porosity and fraction of clay, and we're predicting production. Oh, we're predicting it was an imputation problem of total organic carbon. It was an unconventional setting. Okay. And what we found that was really fascinating was that if we take our biased data and then we take less biased data, and if we take declustering weights calculated with standard methodologies that we all know, and we go ahead and we apply them directly to the machine. Now, in the case of decision tree, that is so easy to do because the decision tree just estimates what the average of the data within the region. Why not a weighted average? Well, when Wendy did this, what she found was that it actually declustered quite well. And what she also found was that if you train with clustered biased data, and then you test with unbiased data, that image, that pattern of bias will remain in your machine, which is very dangerous, okay? But she showed that if you use declustering weights in the machine, it actually had a great reduction in expectation in bias. Okay, so we should be using our same spatial knowledge around biased data sampling, even when we work within machine learning. Bias in, bias out, garbage in, garbage out for machine learning too. All right, I'll have a couple more. I hope your energy is still good. I hope people are still interested in what I'm sharing here. Once again, reminder, if anyone has any questions, comments at any point, I do appreciate that. I will keep watching Q&A window here. Okay, anomalies are impactful. What about spatial anomalies? Here's something really fascinating is Wendy once again took the idea of spatial continuity from the variogram. Now, the variogram model can tell us, given a data point in another location, it can help us estimate the value at another location in space. That's the fundamental Kriging methodology. Now, what's fascinating is she came up with this idea, why don't we use it as a way to assess probability of occurrence of pairs of data? And if you look at it, it's pretty neat. When you calculate a variogram model, it means that for any distance or direction, we can know the H scatter plot. And if you plot the H scatter plot, assuming Gaussian distributions and bivariate Gaussianity, it means you actually know the joint probability distribution function. And so for any pair of data, for a value at the tail location, value at the head location, you can actually calculate where you'll be on that plot, and you can figure out like a symmetric probability of being even lower density, even more extreme value. And you do that, that's like a p-value. Okay, so we go ahead and we can take an available dense data set and a variogram model. We can now calculate the probability of pairs of data occurring. And we can use that as a summary measure. Look at this probability of occurrence. Very cool. So look at this well right here. This is a location map and two-dimensional map. And so at this well, it's purple. That's a low probability of occurrence. You can go to the well and say, what's going on? Well, you don't want to, if you have problems with your data, you got to resolve those up front. You got to do data cleaning. What about this? Oh, maybe we have a facies change. Maybe we have an unconformity. Maybe we've actually had a straddle correlation issue where we're actually sampling a different formation. This is a good idea to check the data and see what's going on. So we can use our measures of spatial continuity to identify anomalies. This is essential in machine learning because many of our machine learning methodologies have L2 norms, okay, which means they're going to be highly sensitive to outliers. Okay, so we got to deal with outliers, and we know stationarity is huge. If you're going into another stationary domain and you're mixing it together, oh man, Simpson's paradox, anyone? Like that's terrible. You can reverse the correlations. You can change everything. It's very sensitive. What about significance of results? The concept of significance is essential to everything we do. You want to do really cool data analytics? Use significance. Use uncertainty in everything you do. Imagine if you sample a pad, are the two pads different from each other? Okay, people who know, the Welch's t-test or any type of t-test for difference in means knows that you can check whether or not two means are dissimilar. You can also do the f-test to check if the variances are dissimilar between two distributions or two sample sets. That's not good enough. This is a spatial phenomenon. We have to do this in space. We have to count for spatial continuity scales. We have to count for location in space. And that's what my student, Jose Julian Salazar, did. Partnered with Dr. Larry Lake, who's well known here in my department. We came up with methodologies for geostatistical significance. Now you can answer the question, I gathered this data here, I gathered this data here. Are they significantly different or are they not significantly different? I can pull them together. If you're going to use geostatistical approaches to evaluate, you can use geostatistical approaches to evaluate stationarity, our decision. We can also use it to see the impact where non-stationarity is poorly understood. Okay, more spatial data analytics. I think we as geoscientists and engineers in the subsurface should be mining all of the great statistical approaches. Okay, everybody wants to do more data science. Everybody wants to do more data driven. Let's look for more statistics. I see a statistic as a new lens to explore the world around us. Quantification is powerful. So one of my students, Mahmoud Shakiba, once again with Professor Lake working on the project, and in collaboration with the Bureau of Economic Geology here, what we did is we introduced the idea of using the Ripley K function, along with some new modifications of it and adaptations to be able to model fracture patterns in the subsurface. We used the one-dimensional measured scan line just near us here in Austin, actually, a close outcrop. We took samples along it, and what we were able to do using this statistic, we did the characterization of multi-scale fracture patterns in 1D. We extended it to 3D also. What we could do is we can simulate brand new patterns. If you're going to do machine learning, you need lots of data. You need to simulate good data for sure. And data imputation. A lot of our workflows in data science require complete exhaustive sampled data. We need to do imputation. Look at that imputation. Very nice imputation honoring the multi-scale behavior. Spatial statistics is a powerful lens, quantification, characterization, and modeling of geoscience phenomenon, for sure. What about training models? I got to tell you, if you're an outcrop-based geoscientist, and that's cool. I celebrate that. I think that's wonderful. Like even in this digital transformation and so forth, we still need the rock hammer. We still need to be at the rock. We need to be looking and studying and learning and exploring this great and vast earth that we have to work with. It's amazing. If that's what you do, an amazing opportunity for you to plug into the digital transformation is training models. It turns out that all of the deep learning methods are hungry for models, and the models have to be good. They have to be good models. If you garbage in, garbage out, that's what we're finding too when it comes to even deep learning and making models from images. And so go ahead, use your knowledge of the outcrops, use your quantification from the outcrop to make numerical models. Here's an example of a distributive, what do we call compensational deep water lobe type of architecture for deep water reservoirs. And so there's a cross section through it. I should also acknowledge that there's many people who have done, Zhang and others have done work on this before. I've done work on it before. Zoltan Sylvester, I'm sure others have done work in this area. But the idea is to be able to make good models. Now we took Kyle Straub, had actually done the compensational index. And so we took his measure to actually compare our model results to actual outcrops and make sure we had good models. When you build these numerical models to power machine learning, you're going to find there's lots of great opportunities to do sensitivity studies. If you're sitting on a library of models, run them through a study, run them through a transfer function. Here we ran them through flow simulation, and we got all kinds of interesting insights. Publish on that. People need these good case studies for sure. What do we learn? Deep learning needs training models. If you're a geoscientist who's working with data sets, consider getting your data ready for conditioning machine learning models. This can be very, very powerful. Subsurface heterogeneity models directly from deep learning? Yes, yes, and it's starting to happen more and more. Anybody ever seen the videos online where people take and they deep fake Tom Cruise? Isn't that funny, where they take a person with about similar, some kind of similar to Tom Cruise, but they make him turn into Tom Cruise. He sounds like, looks like Tom Cruise. That's what we're talking about. The same type of technologies, GANs and more than GANs, we're able to build fake models, which are, we've always called them realizations, right? So we use GANs to have generators and discriminators. We're able to train and make great subsurface models. We use MDS to evaluate whether or not we're exploring the uncertainty space. Look at that. As we train the model, the trained models, the red and the blue models are the input training models. They're actually starting to overlap. We're starting to explore the whole uncertainty space. Very, very powerful methods. We're able to build models. Look at this. We got channel models that are confined by the actual seismically mapped channel complex, or slope valley canyon, they might call it. Right here, the truth model, look at this. After training it, we get channels architecture that fits conditions to the seismic scale information, to the well data. These are really, really powerful models. This is the first time people are able to do this. These models right here, you might as well be looking out an airplane window at a fluvial meandering system down below you. And these are all built with machine learning models, and they're conditional to data. Like, it's exciting what we can do for architectural heterogeneity models. We can truly build multi-scale models now. This is fascinating too. We can build models that honor the architecture at the story scale, the complex scale, the complex set scale, and that's a deep water architectural scheme. But each one of the lobes, and then the architectures within the lobes, and then the architectures within that all honor, none of this cookie cutter approach anymore. Things honor the geometry of the larger scale boundary, the confinement, which is really powerful. What do we learn? We're getting to the point where we can actually build our reservoir models using deep learning. And I think we're starting to understand that these are very powerful. What about forecasting? There are a lot of complicated, computationally expensive transfer functions, right? Like flow simulation could be very expensive, still takes in many complicated reservoirs, like half a day of computational time, even on big resources. So what we've done is we've been working at building models. If you take a lattice Boltzmann and you try to calculate the high resolution velocity field of fluid flowing through this pore structure right here. The pores have been emitted. The remainder is the space between the pores. Yellow is high velocity, red is low velocity near the grain interface, right? You calculate that using a supercomputer. It'll take a day. If you train a convolutional neural net, we can solve this problem with about 10% local error, and we can solve it in a millionth of a second. So very powerful. It actually generalizes. We used it on different types of cementation patterns of grains, and we still retained excellent relative errors. We're peaking out around 20% sometimes. But if you can get that type of error at that type of scale, if you're calculating relative permeabilities, you're doing great. So what did we learn? What are we learning right now? Efficient multi-scale. We just published on a model that works at pore scale, but then we can actually scale it up with the same type of computational speed. And we can actually simulate we're getting to relevant scales for forecasting, like individual units within the reservoir. Really, really exciting. You could change the cementation pattern and see immediately how that affects flow. Let me talk about one last thing and then I'm done here. And that is uncertainty models. Machine learning has neglected this, folks. We in the subsurface, we geoscientists know this, that it is more important to get a good uncertainty model than to get one best estimate. Can we all agree about that the uncertainty model is more important? Because our uncertainty is so important. It's so significant. There's so much uncertainty in what we do. What we've actually been doing with Eduardo Maldonado Cruz is we've been actually tuning machine learning model complexity to match the target uncertainty, not accuracy, not just accuracy, but uncertainty. And we've been building on the method of accuracy plots that comes from Clayton Deutsch at the University of Alberta. He published on, I think, back in 1996. It was a great paper, a great contribution. And so what we did is we've been actually tuning the complexity of the models so that we don't only match accuracy. Look at that. That's a model that's accurate, but by the accuracy plot coming from Clayton Deutsch, that is inaccurate, imprecise. That is not a good model to use. Okay, you should be nearer to the line. Well, we tuned it, we kept the estimation accuracy, but now we have an uncertainty model that's much better. Okay, so what are we learning? We can build ensembles of uncertainty models, ensembles of models using deep learning, and we can tune them to be good uncertainty models. Why? Okay, geostats, you can actually look at sequential Gaussian simulation. You can pose it as recursive application of Bayes' theorem. In fact, sequential Gaussian simulation can be shown to be a good sample of the uncertainty distribution. You can't say that a convolutional neural net is effectively a good sample of the uncertainty distribution. We have to tune it to get the right level of uncertainty. We have to do that by hand, and that's what we demonstrated. Okay, I want to offer a little challenge as I'm finishing up here. If you watch this and you're interested in learning more, I'm going to give you an invitation. I share all my educational content. But to get you started, I have a brand new lecture series I put together, I think I finished up in the past summer. And what it has very basics, like working with tabular data, like our well data, our drill hole data, and so forth. How do we do that in Python? How do we do gridded data, like our maps and our models? How do we do univariate statistics? How do we do bivariate statistics? How do we do, I go through a bunch of stuff. How do we visualize? How do we build models? How do we build pipelines, predictive machine learning models, and so forth? So there's a whole bunch of lectures in sequence that I'm putting together, which use interactive code. And they have interactive code actually, and you can follow along. You can download the code and you can walk along with it. If you want to get started, just take, that's a QR code right there. Pull your phone out, take a little camera shot of that, and you'll be able to go straight to the playlist and get started right now with all the resources you need. Concluding remarks. Subsurface is unique. We have a proud history. It's amazing what we've done. We are the original data scientists. We're further along the digital path. In fact, I spoke I was a keynote at I think it was manufacturing industrial engineers conference in Georgia a little while ago. They wanted me there because they said, we want you to share your reflections from a discipline that's further down the path than manufacturing and industrial engineering. That was fantastic. We should be proud of that. That's really fantastic. We can offer useful insights on the path ahead for the merger of geoscience and engineering. What have we seen? And we've already gone pretty far down that path. Demonstrations, we talked about a variety of methods like artificial intelligence assisted interpretation and how it can benefit from a good framework from geoscience. Domain expertise for feature engineering through the volume variance. There's many things we can do, right? Rock quality index. Training models are essential. Bias and bias out remains. reduce dimensionality for complicated systems using deep learning to make our models. I didn't even show history matching. There's lots of cool stuff we can do. Need to go beyond prediction accuracy to good uncertainty models. For the geoscience, that is essential. We have to do that. Once again, I want to acknowledge, I showed a bunch of stuff by other individuals. Thank you very much to all the great students. I appreciate all the students that I get to work with and all the faculty. And that's it, I'm done. Thank you very much, Alan. And thank you to everybody who joined in.
Well, thank you very much, Michael. Absolutely wonderful. Absolutely wonderful. It shows us we've got a lot of work to do, particularly in EM geophysics, to get to this point. I mean, I was particularly struck by your comment how important the uncertainty model is. In EM geophysics, we find ourselves lucky to find a model, and we often spend a couple of weeks to find a model that fits the data. But you're right. I've always thought this, that uncertainty is as important, if not more important, than the model you find. So I'm going to open it up for questions. And something wrong with my internet. I've got a bit of a delay here, so I hope you're hearing me.
I can hear you, Alan.
Yeah, you're getting a lot of congratulations. Open it up for questions now, please. Anyone throw them in. And Lindsay, if you want to come online, I'm sure you'll have some questions or points to make. Whoa, I think you've thrown so much at us, Michael, that everyone's a bit stunned right now.
I do.
It looks like there's a question that just came in the chat. PV, Michael, there are lots of challenges when working with historical data sets. Can you use data analytics to identify and or classify the quality of the data? Start there, and then his question continues on.
I appreciate that. We said we're going to have variety issues, right? That's part of big data. We said that we're going to have issues with the acquisition changes over time. So we're going to have things happen with the vintage of the data for sure. Recently, I've been working on carbon dioxide sequestration potential in the Gulf of Mexico. And one of our big problems is we got huge data sets to work with, but boy, they changed over time. You can't say the same well log is the same over time, right? And so I'll tell you what, there's a lot of great opportunities around like how we do data checking. And when I showed the example of anomaly detection, one of the first steps to dealing with different vintages of data, historical data, is to find issues, find where things don't match up. And I really like the idea of using spatial methods to detect where we have local anomalies as a way of saying, okay, let's segment the problem first. Let's find out where things are inconsistent, and then we can look at how we can deal with that data. And we know what we do with outliers. It's either going to be removed with great defense, it's going to be transformed, or it's going to be some type of segmentation of the problem and deal with it separately, right? We have our standard geostatistical approaches for dealing with outliers. I think that's one of the things that can help us. The other thing that's interesting to me is that I get really excited about some of the mappings we have. We've been working with autoencoders. And what autoencoders do is they allow us to map high dimensional problems to low dimensional problems. And what we're finding is that when we do that, there's commonalities. There's things kind of start to combine and merge in a way that can be very insightful. And so there may be opportunities through these dimensionality reduction approaches to basically find patterns and then work with those patterns as inputs, more informative inputs to our models. And that can help us kind of sidestep some of these issues.
Awesome. Thanks, Michael. Looks like Chris has got another question. Our independent data sets tend to be quite sparse in greenfield environments. How valuable do you think machine learning is for greenfield exploration?
Yeah, and Lindsay, I really do appreciate that question. That question coming from Chris. Thank you very much, Chris. I just taught a class this morning on Bayesian linear regression. And one of the great things about the Bayesian types of machine learning methodologies is they account for all of the uncertainties simultaneously. In fact, it makes it a very tough problem. You have to use MCMC to solve the posture because it becomes very high dimensional and difficult to work with. But you can account for the uncertainties, which is critical in exploration. You got to account for all those uncertainties. The other thing is when we do exploration, a lot of it's prior. I've done early appraisal before. And what happens, you use all kind of the basin analysis type data, the really gross remote sensing information to come up with kind of really kind of back of the envelope probabilities. And then you go to like appraisal from that step. What's very beautiful about the Bayesian approaches is you do have that cycle of update. And so you can start out very naive in greenfield. And when I say naive, I mean statistically naive, like uniform distributions for your priors. But then you can go ahead and update. And if you're honest, you don't do any information leakage, you can kind of see how the bird beak plot proceeds in a very rigorous manner. In other words, how uncertainty narrows as you gather more data. And so I think that's better than kind of just rough kind of greenfield approaches where we just try to kind of eyeball it. Okay. Now, but once again, Lindsay, if I can, I'm going to also hedge a little bit. And I'm going to say this, greenfield reminds us of just how essential retaining the first, second, and third paradigm when we work in fourth paradigm. Because please don't just try to do data-driven only.
That's a great point, Michael. Leads me to one actually question I have. So you mentioned the role of simulation in potentially, generating training data and using that to augment data that you have. A real challenge with that, though, is noise. Geologic noise is something that we use simulations because we don't necessarily know what that is. So I would be very curious to hear your thoughts and comments on what do we do in that scenario. We've got simulations, but what do we do about making it look real?
Yeah, and I really, Lindsay, I appreciate that. The one comment I'd make is if we're talking about simulation from the perspective of making training images, training models to fuel deep learning. One thing I'd say is retain the kind of expertise or the advice of like Professor Jeff Pyrcz at Stanford, basically a good friend of ours who works in geostats. And I'll tell you what he says. He says, keep your prior really big. Don't narrow the prior prematurely. And so when it comes to, okay, you got noisy data, which means the interpretations can be kind of all over the place, retain that level of uncertainty. Don't overly narrow it too quickly. The other thing I'd say is this, if we're talking about simulation from the perspective of the transfer function, in other words, you have a model and now you want to figure out what's the flow rates and so forth. My dream is TurboTax for subsurface. Anybody here use TurboTax? You know, here in the States, they call it a W-2. I've been away for too long. I forgot what we call it in Canada, but you know that form that gives you what tax you paid, how much you made. You put that into TurboTax, and what happens immediately, top right corner, you get an estimate of your return. And then every time you answer a question after that, what happens? The money goes down. I don't know why, but for me, it always goes down. I lose money every time I answer a question after that, right? I want it to be like that, where you say something about the field, and then immediately you get an update of how that's going to affect recovery factor. You know what I mean? I would love that kind of instantaneous feedback. And I think the proxy models with machine learning are getting us to the point where we can get that kind of like immediate estimation, immediate feedback. In other words, as a geoscientist, should you spend time on that fault? Well, the throw doesn't really matter. You mythbusters it. You take the throw and you make it big. See what happens. Okay, oh, it didn't impact your recovery. Don't worry about it. That kind of thing. Okay, I hope that helps, Lindsay.
Awesome. Thanks, Michael. There's another question for both you, Michael, and Alan. Can we classify EM, e.g. magnetotellurics, as big data?
I think the background to that question is that in most of electromagnetism, geophysics, we're seriously undersampling because it's such expensive data to acquire. And then once you have your sites, it can take 2 weeks to do a 3D inversion and come up with a model. Now, there are a few people that are doing probabilistic inversions, but not enough. And so a lot of the techniques you've been talking about today, we would struggle to apply in electromagnetic geophysics at the moment.
But Alan, can we call it big data?
I think so, yeah. According to what you told us at the beginning, yeah, it hit all of those. Yeah.
Yep. So, hey, everybody on the line, update your CV. You do big data analytics.
Okay, I'm not seeing any more questions. Lindsay, do you have any Anything
Well,
else?
just a big thanks to Michael, and also I was so thrilled with all of your open source resources and lectures. I've certainly benefited a lot from those, and I know many others who have been. So a big thanks for that.
I got to tell you, that cheers my heart. I love to hear about people finding value through it. The role of a professor is a role of service to society, right?
Yeah.
We're all in it together. Industry, students, faculty, we're all working together to push our practice, to make sure we have the best practice to use the subsurface resources.
Well, you're getting an awful lot of congratulatory claps, and even one heart I just saw went up.
All right, awesome. Hey, thank you very much. What a pleasure. What a treat. Thank you so much for letting me join in.
Thanks very much for giving this, Michael. And this recording will be on the YouTube channel in a couple of hours. And Michael, if you could send me the PDF, please, and I'll put that up on MTNet.
All right, awesome. And I'll tell you what, I'll promote the YouTube too through my social media.
Thank you.
Okay.
All right, bye everybody, and I'll see you next Wednesday.
All right. See you all.